Turn it on. Okay, so now it should work. Yeah? Okay, I'll get started because it's supposed to work now. Okay, so first one, is there an effect of species, is there an effect of pH and biomass on diversity? And diversity is the variable species. And these data are stored in df1. Okay, so what I did, for the people who couldn't hear me at the beginning, I downloaded the data set, I downloaded the R Markdown file. They're in the same location, so I opened the R Markdown file and did session, set working directory to source file location. Now that does this, set working directory to something, and that tells R where to find things in case I ask it, read this, load that, etc. So then I ran this, and it knows where to find it because I just told it, and that opens 3 data sets in the working space. So the next thing we're going to do is answer this question. So we have the pH, the biomass, and the diversity. Well, diversity, from the word itself, you can't really hear what kind of outcome it is, so let's just have a look. We have pH, which is categorical. It's either low, mid, or high. We have biomass, which is a continuous outcome, continuous variable. And we have species, which is very clearly not continuous because they're only whole numbers, and you cannot have 1.5 species. So this would be what kind of outcome? Yeah, so that's the probability distribution. The outcome is a count, and the probability distribution would be Poisson. So I'm going to fit a model. I'll give it a name. You can name it whatever you want, but I just call it GLM, so remember what it is. And then the outcome is species. And then I do tilde. I'm going to put the phone somewhere else, otherwise I can't really type. pH plus biomass. Yeah, let's see if I remembered correctly what they were named. Yeah, biomass with a capital B, etc. Okay, and where to find it? So first family is Poisson in this case. And the data is df1. Okay, I run this, no errors yet, so that's good. And then we're going to produce a summary, because the first question is just, is there an interaction? Well, that's very easy to see. We produce a summary, GLM, and it gives us a bunch of outputs. Namely, I will go over this completely for several examples so that you can see what this is, see how it's similar to linear regression, and see where it's different from linear regression. First, it just repeats what I did. So it just says, okay, this is the formula you used. And then it says deviance residuals. Anyone have an idea why it says deviance? What that might mean? It's kind of in the name. Yeah, it's a different word for variance. Now, it specifically doesn't say variance because exactly, because it's not normally distributed. So for the normal distribution, we have a mean, which is the location, and we have a variance, which is the width, so to speak, the spread of the normal distribution. But these are the parameters of the normal distribution. I fitted a Poisson distribution that only has one parameter, lambda, and lambda is the mean and the variance of that probability distribution. So there is no meaningful squared difference from the mean, which would be variance. So we don't look at the variance. So what we do instead is we look at the deviance, and in that case, if this default GLM is right, then it should be more or less symmetric for count data. So again, we can use diagnostics, which is way better, but this shows the minimum, the first 25%, first 50%, first 75%, and the maximum. If the minimum or maximum are really different, then there might be an outlier. And if the first 25 and first 75% are very different in size, then it's asymmetric. So you might want to try a different link function. Okay, so that's more or less the same as with linear regression, except that it's called deviance. Then we have the coefficients tab. This you can interpret mostly the same as for linear regression, except for the value of the estimates. That's what I'm going to talk about now. This gives you the values of the estimate on the scale of the linear part. Yeah, but we applied a link function. So if we want to calculate what is the intercept on the original scale, we have to undo this transformation. Now we applied the default GLM, which is canonical link function, the Poisson distribution. Yeah, the logarithm. And what is the inverse of the logarithm? Yeah, the exponent. So if I want to know what is the intercept in terms of counts, you know, where do the counts start? If I plot this on the original scale, then I have to do the exponent of this intercept. Yeah, this won't be on the exam, but I just want to show you what is going on here. So this says that actually the intercept for the counts at about 47, right? Not at 3.84 something. That's on the scale after applying this logarithmic translation. Okay, then it says if your pH is low, it is minus 1 point something, so it's 1.1 lower than the intercept. Yeah? So anyone have an idea how I can get this one back on the original scale? So if I want to know what are the expected counts for low pH. Okay, let's take one step back. On the scale of the linear part, the intercept is 3.8. What is the expected value for pH low? Approximately.
384 minus the 1.
Exactly, yeah, that means I have to make it bigger. Yeah, so on the linear scale, the value for low that we expect is this plus this estimate over here, yeah? But there's a minus, so it becomes negative. But this is what we expect on the scale of the linear part. Now, if you want to know what it is on the original scale, then you have to take the exponent of this entire thing, yeah? So not just minus 1.13, but of this entire thing. And then we see, okay, for low pH, the expected count is 15. Yeah, that's how you can work with GLMs and report things. It's not always necessary. If you just want to know, is there significant effect? These p-values will give you the answer. But if your question is, okay, but what then is the expected count for this group and that group? This is how you can do that. Now, then the more tricky one, biomass is a continuous variable. So let's say I have a biomass of 0.5 and my pH is high, which is the reference group. Then how can I get the estimate on the scale of the linear part for that? Yes?
First do the exponent of the intercept and then plus the biomass.
Times?
Plus.
Sorry?
I thought that you have to do like the exponent of the intercept to get the actual value.
Yeah, so the exponent we need if we want to get back on the original scale. But on the scale of the linear part, if I have a biomass of 0.5, then what do I expect the value to be for pH high? So what's the formula? The formula that we wrote is we do species as a function of pH plus biomass. So what we're really doing on the scale of the linear part is we say we have an intercept, that's this one. Yeah, and this is the intercept for pH high, right? Now, the intercept is where biomass is equal to, sorry? 0, yeah. That's what the intercept means, right? It's the starting point, the anchor point. So it's like doing 0 times this value for the slope. Yeah, which is just the same value. But if I want to know, okay, if I have a biomass of 0.5, then I just add this value. Yeah, this is what I multiply the slope with. Yeah, or more in line with how you learned it. Intercept plus slope times explanatory variable. Yeah? This is the estimate on the linear part. And again, if we want to know what is the estimate on the original scale, then we take the exponent, because the exponent of the logarithm I'll just draw the numbers 1 to 100, and you'll see that is the numbers 1 to 100. That's the inverse transformation. So the exponent of this will give us the actual expected count for high pH biomass equal to a half. Yeah, which is 44. And that's how you can work with this. It's not part of the course, so don't worry about reproducing this. But you can go even one step further. You can produce confidence intervals, and even those you can transform back on the original scale. I just wanted to say that because it's really useful, and it's probably what you want to do in your internship rather than just only looking at p-values. But for the exam, you don't have to know that. Okay, let's continue with the question. Oh, yeah, sorry, let's continue with the output first. That's the estimates, right? Now, standard errors is just a measure of uncertainty of this estimate. What is the question that we ask in these types of models? It's, is my coefficient significantly non-zero? Because if it's 0, it's the same as saying it has no effect. Now, the way to do that is to divide the estimate by its standard error, which is a one-sample t-test. And for GLMs, it calls it z-value, but you can just interpret it as a t-test. And then we ask the question, what is the chance of getting this large a test statistic if the null hypothesis were true? So if this coefficient in the population were 0, the slope, the intercept, whatever, what is the chance of getting this large a test statistic? Now, that chance is incredibly small. It's 2 times 10 to the power of minus 16, or less than that even. So we reject the null hypothesis and we say there is a significant effect of biomass, because the chance of finding this large an effect of biomass, if it had no effect, is really small. Yeah? So that's the coefficients tab. Then we see dispersion parameter for Poisson family taken to be 1. This has to do with over dispersion, and I'm not going to explain that now because Harold will explain that tomorrow. But very short, the Poisson distribution only has one parameter, right? And it represents its mean and its variance. But for some count data, there is some unknown thing that also contributes to the variance. And that causes what's called over dispersion, which means that the variance is actually larger than lambda. That's a problem because the Poisson family only estimates one parameter, so it cannot encompass larger variance than the mean. So what you would have to do is use a different kind of model, but again, this is what Harold will tell you tomorrow. Then we see the null deviance. Now again, we see deviance and not variance because we're working with a distribution that's not normal. So here the deviance, if we the null deviance means if I just fit an intercept, so I'd have no explanatory effects, then this is the measure of dispersion, the measure of variance for the Poisson distribution of 452. Exact value doesn't really matter, but what does matter is how much of that dispersion is left after fitting this model. Yeah, and just like when we have R squared for normal models, we can say the variance explained. In the same manner, you can divide this residual deviance by the null deviance to get an estimate of how much of the dispersion has been explained, how much of the deviance has been explained. Yeah? Now, and we see degrees of freedom again. So here we have the null deviance. I just told you that's a model without explanatory variables, with only an intercept. So that costs 1 degree of freedom, and we have 89 left. So this model had 90 samples. Other way to see it is residual deviance. That is the deviance left if we fit our model. That one has 86 degrees of freedom left, and we have an intercept and 1, 2, 3 slopes. So that's 4 degrees of freedom used. So it means that our sample size was 90. Now, then finally, R is nice enough to also show the AIC, so we don't have to compute it manually, which is useful if, for example, you are in doubt, should I use this link function or that link function? Should I include an intercept or not? Because then you can compare the AIC values of models, which give you an idea of how poorly the model fits. So you want this value to be as low as possible, and how complex the model is, and you want it to be as simple as possible. And the combination of two give you AIC, meaning that the lower AIC is the better model. Yeah? Okay, and then we see number of Fisher score iterations 4. This is not something that you will ever have to use, I think, but let me just explain why it says this. With normal linear models, there is a direct way to calculate the coefficients, right, with this least squares. With a generalized linear model, that doesn't exist. It follows some iterative algorithm, and it gets an initial estimate, then it updates it, and it gets another estimate, updates the weights, and this iterative procedure will cost you, several times running through the algorithm. It just says how many times it took it to get to the result. If you get an error like convergence not reached, then what you can do is you can look at how many iterations were performed, and maybe you can set the number of iterations higher. I'm not going to show it here because we're not going to do it in this course, but it's possible to increase the number of iterations, and then maybe it will converge. So that's what it's for, but again, I don't think you're ever going to use it. Yeah, so that's the entire output of a GLM. Okay, let me check for questions. Nothing yet. Then let's continue with the exercise. The first question is, explain your choice. We already did that. We have count data, so we want a Poisson distribution, and we fit this model. I have no particular reason to assume an interaction. If you plotted your data, you could get an idea, whether interaction makes sense or not. So you could do that to see, do I need an interaction? So let's do that. We're going to plot the number of species against pH and biomass. Well, that's not going to work, of course, because we can only plot in 2 dimensions. So what I'm going to do instead, I'm going to plot species against biomass, and I'm going to color by pH. Yeah? And I think this may be, okay, so this is stored as a character, so there should actually be one step preceding this. Let me just move this. The first thing you should really always do is to check the quality of your data, of course, and see, are these read correctly into the software. And the answer is actually no. This is read as a character, where this isn't text. This represents classes, high, low, and medium. So I want to convert it to a factor. So df1 $pH converts to factor df1 pH. Now we should be able to do this if I say where it can find these variables. So data is df1, and then I see this. Let me make these filled, because that makes it a little bit easier to see on the screen, I think. Over here, pH is 19. So, okay, this is our plot. If I am to imagine a curve through here, because we are going to take the logarithm, I don't think they will have a different relationship. I see more or less the same trend in all of these. So based on this, I wouldn't be convinced that I needed an interaction. However, we're of course going to apply a link function to this, right? We're not actually drawing lines through this, but we're drawing lines through the transformed version of this. So we can plot that too. Then we take the logarithm of species. Now, this may return an error. I have to check. Oh, no error. Okay, then I'll explain it later. And now we can check again. If we were to draw a line through this, which is what the model's actually looking at, right? The logarithm of it. Do I still think these lines are parallel? Now it actually looks like there might be an interaction, because the red trend is much more steep than the green one, which in turn is a little bit more steep than the black one, right? So, let's add an interaction and produce another summary. Now, the interpretation is almost the same. All of this is the same as before, except that now, we use a little bit more degrees of freedom because we have more effects. There's a little bit less residual deviance because we have more explanatory effects, so it will explain more of the deviance. And we have 2 new estimates over here, which is the estimate for the interaction low biomass, mid biomass. Now, how to interpret this? There is a reference group, right? If you don't specify anything, it will use the first letter in the alphabet, which happens to be H. So pH high is the reference group if you don't change it. That's fine. Then it compares everything with pH high and a biomass of 0. And it says, okay, if your pH is low, you start out lower. If your pH is mid, you also start out lower. And it says for every unit increase in biomass, if you are pH high, you will go down by 0.1, right, on this scale. But then it says if you are actually pH low, then the slope of biomass is 0.15 lower than this slope. Yeah, so the actual slope for pH low is 0.10 whatever. Let me just copy that. Oops. This one plus the interaction effect, yeah, because you are both increasing the biomass and you're changing the category pH low. So then this is the estimate for the slope. And that's what we saw indeed, that there is a steeper slope for the other two groups. Then we have this one, which is also a little bit steeper, the slope, steeper down I mean, but this one doesn't differ significantly. So yeah, this one we can also calculate, it's just the previous one, but then minus this. Yeah, and then it says, okay, this slope of 0.14 doesn't differ significantly from this one. Yeah, that's the three slopes that we observed over here. The red one, the steepest one, well, that has to be low then, because that one had the steepest slope. And we have mid, probably this one, and we have high, probably this one. Yeah, if you use R a lot, you will know that the coloring, if you don't specify the colors, will be in the order black, red, green, blue, and then something else. So this is actually the first group, this is the second group, this is the third group. Easier way to know that than just learning by heart how R specifies things is to produce a legend. So let's do that too. I'll make a legend, and okay, where do we have space in this plot? Maybe in the lower left corner. Sorry, bottom left it's called. And the legend should be the levels of this factor, so df1 pH. And then I say colors should be 1 to 3, and the point character I want to be the same as in my plot, and I use number 19, which is a solid circle. So I do that, and I have another look, and it looks ridiculous. Maybe V interspace or something. Oh yeah. Let's set this to 0.1. Okay, look, that's better. So we run it again because if you remember from the first week, if you use base plot, it will plot everything on top of what you already have. So if you want to get rid of the old legends, you have to rerun it. And then it looks like this. Yeah, still not beautiful, but it gets the point across. Yeah. If you want to get rid of the box, works the same way as for the plot function. So you can just do box type is nothing. Oh, let me adhere to the Google style guide there. So one more time. And I have a plot like this. Yeah. Again, it's not a great plot, but you know, I don't want to spend too much time here live making this look good. But it does show you what we're looking at. Yeah. Okay, there's a question. pH high and pH mid differ significantly from 0, but does your summary prove that the interactions differ from one another? Okay, so they do differ, but the summary over here says that mid does not differ significantly. Now be careful with the word prove, because you cannot prove anything with data, you can only make it more likely. This data says that it is very unlikely that a population where pH low and pH high have the same slope produced this data. So there we reject the null hypothesis and say, okay, there is a significant difference between pH low slope and pH high slope. This one doesn't differ significantly. Yeah, so even though it's lower, it's not significantly lower. Yeah, you can see that by looking at the column that says probability of getting an absolute value of z or greater, which is the p-value. Okay, let's see if there were other questions. Yes.
Could you re-level the pH? Because I think that changes the interaction of the pH mix.
Oh yeah, sure.
Could you
Yeah.
re-level pH low?
Okay, I will do it below so we can see both of them. Okay, so the way to use relevel is just to fit your model again, but then on a version of your data where the order of the factor is different. You can do that like this: df1, ph, overwrite with df1, ph. Yeah, but now I want to have some space to type. I want to relevel this. Yeah, and then you say, okay, what do you want to relevel? This has to be a factor, so this will only work if you already converted it to a factor. And I want to have as reference group, what shall we do? Low. Okay, then I do this, I run it again, I produce another summary. And then we see that the interaction is different, right? Anyone have an idea why? In the previous example, wait, which one did we look at? Yeah, in the previous example, mid was insignificant. Now I re-leveled, I made low the reference category instead of high, and now it is significant. What does that mean? Yeah, it's a different comparison. We're comparing mid to low now. So this is a completely different comparison than this, because this shows the difference between high and mid, because that's the first letter in the alphabet, the H, and this shows the difference between low and mid. So what this tells you is that high and mid do not differ significantly, high and low do differ significantly, and mid and low also differ significantly. Yeah, and low and high we can also compare with this one. Yeah? Does that answer your question? Okay. Okay, write a short conclusion. No, I already told you how to interpret it. I will write a conclusion post on Brightspace, but let's not waste too much time on this example and also have a look at another one. Anyone have preference for a particular exercise to see it live? I will also look at my phone. So if there was any exercise from yesterday or the day before that you found particularly difficult, we can have a look at it now. Yes? The? Okay, parasitic infection. Is everyone okay with that? Because we'll have a limited time. Okay, I see some nodding. We will do parasitic infection. I don't know which one that is, so let me, parasites. Oh yeah, there we are. Parasitic infection. Okay. Is parasitic infection in a certain animal species more common in males or females? What about older or heavier subjects? And the data are stored in DF3. Okay, now I'm actually going to do it in the right order. The first thing is to check the quality of your data. Has it been read correctly into R? So, structure of DF3. We have infection. No, this one's not read correctly in R. It is read as a character, which caused a lot of frustration. And age is an integer. Yeah, sure. Weight is an integer. Well, apparently it was rounded in this data set. And sex is also a character. We want it to be a factor. We want R to know this is not just some text, but this text has meaning. It belongs to certain classes. So first step, fix the data. So infection is gonna be a factor. Second one also, I'm just gonna copy paste this. Sex should also be a factor. Okay, this will actually solve most of the issues that I saw people have. In the graded assignment, I will remind you to have a look whether things are read correctly into the software, if it poses a problem at all. Okay, so I run this, and now if I run the structure again, I'll see that indeed infection is a factor with 2 levels, correct. Sex is also a factor with 2 levels, yeah? Then, the first thing we're going to do is we're going to make a plot, right? Because we're doing it in the right order now. So let's see what we can plot. We want to know whether parasitic infection is more common in males or females. This is really hard to plot because there's only 2 possible outcomes. Either you had parasitic infection or not. So I can only plot on 2 locations, 1 and 0. That's a bit hard to see. So I'm going to use a trick over here. There are different ways to plot this, for example with some sort of mosaic plot, but first I'll show something that I would do if I have binary data and I want to have a look at it. So my outcome is still going to be infection, right? Because that's what I want to see, binary or not. Then I want as an explanatory variable, again this is, you will have to do this in stages because we cannot plot in 3, 4, 5 dimensions. So let's plot it against the age first, yeah? So here we have age, and then I say I want to color it by, oh yeah, actually we can do it very simply. We can color it by weight maybe, or okay, I will put a nice solution to this online. I will now do a crude solution. I'm going to color it like this and say that the data is df3. Okay, what happens if I plot this? Let's first see whether it works at all. It does, but this is probably not what we want. Yeah, so why does this happen? Yeah, it just shows absence and presence and colors in both black. Very useful, thank you very much, R. Let's try something else. Let's force this to be numeric. As numeric infection. What does it look like then? Also not great, but at least we have the actual data plotted here, right? But it says 1 and 2. That has to do with the way that R stores factors. Not something you have to know. I'm just showing you that it is the case. Yeah, it stores a factor like this. Oh, sorry, df3 I want to look at. Yeah, this one has 2 levels. It's either 1 or 2. Yeah, number 1, number 2. But you know, we want to see zeros and ones because that is what, yeah, how we interpret this. So the way to do that is I will just create a new variable. It's easier. So outcome y is this minus 1, and that will be always equal to 0 or 1. Oh, not found. df3 like this, yeah? So if I run this, I will have a vector with a bunch of zeros and ones, and then I can plot this y against age. Okay, and I can see, is there a difference in, yeah, red or black depending on age? It's really hard to see. So this is where the trick comes in. First thing, let's fill these up. 19 is easier to read in my opinion, and then I'm going to use a function called jitter. What does jitter mean colloquially? Yeah, you know, when you're jittery, you're shaking. So jitter means to yeah, spread everything out a little bit randomly. So if I do this, now it looks like this, which is way better because now any overlapping values can be easily told apart, and you know, we can still see, okay, these are the zeros, these are the ones. So this is already a little bit helpful. But it's still quite hard to see, you know, is there more, yeah, red compared to black here than here? I don't know. So I will try and post a solution where there is a more informative plot, but the real thing to do would be to plot your model here. Because when you fit a logistic regression or a binomial GLM, which is a different name, it's just a binomial GLM, what it actually estimates is an S-curve. And if you plot that S-curve over your data, you can see the different S-curve for red and for black. It cost me a little bit more time to do that because I don't know by heart how to do it, so I will post that solution online. Now I will just show how, okay, we might not see it here, but we can see it in the model. So let's there might be an obvious difference with weight, so let's create that one too, just in case. And then we have the weight against jittered y. Here we can actually kind of see that there is indeed a lot more red where weight is higher, and there appears to be more, yeah, more black over here. But it's still not super clear, so I will post a nicer solution. So let's get to the actual model. We have a GLM. What kind of data is this? Yeah, why is it binomial? Yeah, it can be absent or present. So the way you can interpret that is that it's the number of successes out of one trial, right? And the trial was either successful 1 or unsuccessful 0. Binary data can be fit with a binomial GLM. The way to do that is like this. infection. This will only work if infection is already a factor. And then we say, okay, we have the sex, we have the age. Do we have anything else? I don't think so, but yeah, I think this is it. Weight, okay, great, thank you. Weight as well. And we have family is binomial. And we have to specify where R is to find it, so data is df3. Okay, I fit this model, and let's look at the summary. Now, what does this show? Again, this shows the estimate on the scale of the linear part. So this is after the logit transformation, because we didn't specify anything, so use the canonical link function, and the canonical link function for a binomial distribution is the logit. So these numbers are a bit hard to interpret as is. If you want to know how to convert this into numbers, again, not part of the course, but this will be useful for your internships. If you want to know how you can convert this back to actual proportions, you know, between 0 and 1, the way to do it is to get the inverse of the logit. You don't have to remember this, but it is the exponent of something divided by, what was it, exponent of something plus 1. Let's check. So, how would you find this if you didn't know? There's a great site called Wolfram Alpha, which is a computational knowledge engine. This will do math for you, which is really nice. So, we just ask for the inverse of the logit transformation, and the logit was the log of p divided by 1 minus p. Again, not part of the course, just showing you how you can do it. Okay, it has determined that the inverse of this, is it finished yet? This isn't correct. Oh yeah, there we are. It's the exponent of p divided by the exponent of p plus 1. Yeah? No need to remember this by heart, but yeah, if you have to use it a lot, then it's useful to know by heart. So, there we go. What do we fill in there for p? Yes? Yeah, the estimate. So, let's start with the intercept. What is the base rate of this occurring? That's what this answers. That is, 65% chance of a success. Yeah, and in this case, what is success? What is failure? Let's see. We will have to look at this. DF3 infection. The first level is taken to be the 0. Second one is taken to be the 1. So the chance of presence of parasitic infection, some baseline measurement for the intercept for the reference group, is apparently about 65%. Yeah? If I want to know what's the difference for males, how do I do that? For males, what is the rate of parasitic infection? Yeah?
So in between brackets, we just have to put the first estimate minus the estimate for sex male, and then the result of that will be calculated.
Yeah, exactly. So I want to apply this entire back transformation to the sum of the intercept and the estimated slope for males. So let's do that. I'll just paste it over here, and I'll copy the estimate for this. And Control V. Yeah, so what I'm really doing is I'm adding estimates. So I'll just to be absolutely clear, I'll do plus the negative slope like this. And apparently the base rate for males is much lower, with only about 28%. This is nice, right? Because if this is your research, yeah, okay, you can answer which of these had a significant effect. But from these numbers, it's really hard to tell anyone what was actually going on. Again, this won't be asked in the exam, but I just want to show you because this is what you will probably be doing if you use this for your internship, which is to transform it back on its original scale. Now, the lecture today was about the link functions, right? And canonical and other link functions. if the purpose of your study is just to do a significance test or just to get a predictive model whatsoever, try link functions. Try another one, see which gets the best fit. What I'm doing here, back transformation, is only possible with the canonical link function. If you use a non-canonical link function, like I could have used the complementary log here or the probit or whatever, then the calculation back to original scale is much more difficult and not something I recommend you waste your time on. So if the purpose is having an idea of what the estimates are on the original scale, use the canonical link function. You know, it's called canonical for a reason. It is the default choice for a reason, so go with that. Okay, let's have a look at the question. Could this also be with a Poisson GLM with the outcome as counts of infected and non-infected number of cases? Yeah, you could do that, but there's a problem with that. Can anyone imagine what that might be? So let me just show the data set. His question is, why don't we just, can I make this bigger? Yeah. Why can't we just add all the absent and present ones and turn this into a count and consider it to be Poisson distributed data? You could do it, but what would be the disadvantage? Yeah?
Maybe you don't know about the details.
What do you mean by that?
Yeah, I can explain. I'm not sure.
Okay.
Just repeat the question, please.
Okay, I will repeat the question. Let me show what I mean. Why don't we do this? Why don't we add all the absent and present cases, so DF3 infection, DF3 H, by this one, yeah, and the rest are left. So why don't we work with these counts and then see, okay, what is the difference between males and females? Yeah, why don't I just add all the absent and present one and use Poisson distribution?
This might not make sense, but I would intuitively say that when we use sample size.
Yeah, you are drastically reducing your sample size. That's one reason. Because you're pretending that it's one observation of a particular count, where in reality, these are separate observations. There's another, perhaps more important reason in this case. If you only have categorical variables, yeah, you could sum them per combination of category. But how am I going to add an absent H2 weight 1 to an absent weight H15 weight 16? There is no meaningful way to add those observations, and the only way to add them is to disregard their age and disregard their weights, which is throwing away a lot of information, and it makes it impossible to say anything about the effect of age and weight. So you could do it. You could turn this into a contingency table, or you could, turn them into age categories, but you are throwing away a lot of information, so I don't recommend it. Yeah? Yes?
We can also lose degrees of freedom.
Yeah, definitely. If your sample size is lower, the degrees of freedom that you have are lower, so you can also use a less complex model. Okay. Which variables affect the probability of infection? Then let's look at the summary once more. Well, anyone have an idea? Yeah? Yeah, weight has a very significant effect and reasonably large estimate, because this is for a unit increase in weight. And if we look at weight, let's do this. Plot DF3 weight. Hopefully that'll give me a box plot. No, it doesn't. Then let's turn it into box plots. Yeah. Weight actually ranges all the way from around 0 to around 20. So only an increase by 1 already has a substantial effect on the outcome and a significant effect on the outcome. So weight has a pretty large effect, because you could have a weight of 10 larger than another individual. What else? Any of the other variables? Yes? Yeah, and which one has the greater chance of parasitic infection? The? Why? Yeah, so it has a significant effect. That's what we can see over here. That's just the p-value, right? But if I wanted the direction of effect, I have to look at the estimate. Now, logit, although it's a silly transformation, a bit strange to interpret, it is still monotonic, meaning that what is an increase on this scale is an increase on the original scale, vice versa. So that means if sex male has a lower estimate than sex female, then apparently it has a lower probability of parasitic infection. Yeah? So, males have significantly lower parasitic infection. The higher your weight, the lower the chance of parasitic infection. I don't know if this is realistic, this data, or not, but yeah, that's just what it says. And finally, age seems to have a very slight positive effect, but it's bordering on not significant. And if we would correct this for multiple testing, then it would definitely not be significant. Okay, last question. If I would correct this for multiple testing, how many tests did I perform? Yes. And why is that? Yeah, that is correct. But the research question asks what is the effect of male female, what is the effect of being older or younger, what is the effect of being heavier and lighter. In other words, as is very often the case, the intercept is not of interest to the research question. So yeah, we don't really care. What does this p-value even say? It says, does the base rate differ from 50%? Who cares, right? So the three tests that we're interested in is there a difference caused by sex? Is there a difference by age? And is there a difference by weight? So I would only take these three p-values, which is perfectly fair because you weren't interested in this one in the first place, and correct only those for multiple testing. Yeah?
The intercept is the sex female.
Yeah.
Right? If you're interested in the difference between male and female, so you want to do the split between what?
Yes, but a p-value tells you the outcome of a test for a difference. So what does this difference say? The difference of what? Females versus? Sorry? Versus? So the reference group is females. What is the intercept compared against? But females minus females is 0. What do we usually compare the intercept to? And what is the value under the null hypothesis? Not 1. It's 0. Right? If a coefficient is non-zero, it's significant. So this test is meaningless because the only thing it's saying is, is the base rate for females on the logit scale significantly different from 0? But that just means, are females significantly far away from a 50% chance of parasitic infection? That is not part of the research question, so why would you use that test? Yeah? To compare males and females, that's two groups. That's only one comparison, right? If there is a difference caused by being male, that is the difference between males and females. Yeah? Okay. We don't have a lot of time left. Were there any other questions about the assignments? Otherwise, I will go to the other building, and then in the evening I will try to make some solutions. Okay, how far is everyone? Did anyone finish everything from linear regression and GLM? You finished everything? Okay, did you also try different link functions and compare? Okay, good job. What kind of understanding of GLM for the exam do you need to know? Okay, the level of understanding for the GLMs for the exam is what I covered in the lectures. So there's a reason I kept the lecture short. We're all the way up to multiple linear regression. I think that you should know a little bit more than just the basics, right? But for GLM, you should know what is it. So a three-part thing, an error structure, a link function, and a linear part. And you should know which probability distribution belongs to what kind of data. So we only use 3 in this course: normal, Poisson, binomial. And you should know what is the canonical link function of the Poisson and the binomial. Yeah, so that's the log and the logit. If you know that, that's enough. Yeah, and of course, be able to recognize that when an output says dispersion parameter and null deviance and deviance residuals, that this is not a linear regression, but a GLM. Okay, let me ask my previous question a little bit differently. Do you need more exercises, or is this enough? Some more? Okay, then I will produce some more. Okay, that's all for today. If you already finished, then yeah, nice. You'll do fine. But otherwise, I will hopefully this evening upload some new assignments.